Let's continue in the next section. I put in a couple more examples to look at. This is for the direct comparison test. And then we did the limit comparison test. Here and here, I put in a few more examples if you want to try them for the limit comparison test. Okay, let's go on to 10.5. This is on what's called absolute convergence and the ratio and root test. So first we want to define what we mean by absolute convergence. So we say the series A sub n is absolutely convergent or converges absolutely if the sum of its absolute values is convergent. So you're taking the absolute value, and so we say it's absolutely convergent or converges absolutely. It's the concept. So then there's a theorem that says basically if the series of absolute values of each term converges, then the series must converge. So basically it kind of has to make sense, right? If you have negative values in here and you're adding them up, but the absolute value of that converges, then the negatives are just going to take away from the sum, and it has to also converge. So is the converse true? That's the question. I'm going to jump ahead a little bit to the next section because I don't really like the order they put this in, but we'll do more on the next section, 10.6, later. But I did throw down here the most important theorem in that, and that's called the alternating series test, which is an interesting result, I think. So if A sub n is greater than 0, the alternating series, and you can start at whatever number, but basically it alternates, A sub n converges if 1, the limit of A sub n equals 0, which has to be true, we showed that, and A sub n plus 1, the next term, is less than or equal to the previous term. So in other words, the series is monotonically decreasing. So if you have a monotonically decreasing sequence, limit approaches 0, then the alternating series converges. If it wasn't alternating, that's not true, right? You can show counterexamples for that. So we want to look at, for this one, and consider the harmonic series. So the harmonic series we know diverges, right? But what about the alternating series? Like if you have that alternate, what happens? So that's really the question. Well, we know that 1 over n is positive for all n, right? We know that the limit of 1 over n is equal to 0 as n approaches infinity. Okay, and then we also know that 1 over n plus 1 is less than or equal to 1 over n for all n. And then, etc. So because that's all true, by the alternating series test, so therefore by the alternating series test, we would know that negative 1 to the n of 1 over n converges, which is an interesting result, right? So this converges. Does it imply its absolute value converges? Right, so if you take its absolute value, does that converge? Well, if you do that, then you get just 1 over n, and we know that diverges. So the converse, if this converges, does it imply that the absolute value converges, is not true. Right, so the converse is not true. Okay, so that's false. So just only one direction. Okay, let's go on to the next ratio and root test. Okay, so this is the ratio test. So next theorem, I guess it's theorem 13 in the book. This is called the ratio test. So for the ratio test, let's let a sub n be positive for all n. And then we're going to suppose that the ratio, so you take the limit of a sub n plus 1, so you're going to add plus 1 to each term, over a sub n, as n approaches infinity, equals a L. Then you have, so it equals a fixed value. Then you have three possibilities. One, if L is less than 1, the series is convergent. The series is convergent. 2, if L is greater than 1, or it approaches infinity, or the limit of a sub n plus 1 over a sub n the series is divergent. And 3, this is the one you don't want to have. If L is equal to 1, what would you say? There's no conclusion. Apply a different test. Okay, so let's look at a couple examples of that. Let's look at so determine convergence or divergence of the series n equal to 1 to infinity, n to the n over n factorial. Okay, so then apply the ratio test. So what you need to look at then is you have your a sub n, right, is the n to the n over n factorial. So a sub n plus 1, you replace n with n plus 1 everywhere you see that. So that's n plus 1 raised to the n plus 1 over n plus 1 factorial. And then you're going to take the limit of that, you're going to do that ratio. So you need to, basically what happens, you got to simplify a bunch. All right, so let's take a look at the limit. Does it satisfy the hypothesis? Basically, yes, because it's positive. So the only real issue here is that you have positive term sequence, and that's true. So we have the limit of a sub n plus 1 over a sub n as n approaches infinity equals the limit as n approaches infinity. So then you have a sub n plus 1 divided by a sub n. So what we're going to do is invert and multiply that. So this will be n plus 1 raised to the n plus 1 over n plus 1 factorial times, and you end up with n factorial over n to the n. And so we want to simplify that down quite a bit. So when you simplify that, remember what everything does. So n factorial is n factorial is n minus 1, all the way down to like 3, 2, 1. Okay, so just keep that in mind. So n plus 1 factorial is n plus 1, and then it's n, and then all the way down to 3, 2, 1. So everything's going to cancel out and reduce. So you end up with just n plus 1 into the denominator. So that's equal to the limit as n approaches infinity. Just move this out of the way. Of n plus 1 raised to the n plus 1. Oh, and see if, go ahead and pause this and see if you can simplify this this whole thing. There's a lot of algebra going on right now. And then that's times 1 over n to the n. So all I did is simplify the factorial. Okay, so keep going. What you have then is this is equal to the limit of n as you approach infinity. Okay, then you have the n plus 1, so this is like a 1 here, so you end up with n plus 1 to the n. So it's n plus 1 raised to the n over n to the n. And you can raise that all to the n, which is the limit of n plus 1 over n, all raised to the n. And then we can simplify the inside, which is the limit as n approaches infinity of 1 plus 1 over n, all raised to the n. Now, that is a special limit. Look that up. What does that equal? That equals e. Isn't that cool? Okay, so that equals e. So what does that tell us about the limit comparison test? E, we know, is approximately 2.718281828, and then it does not repeat after that. And so it's greater than 1. Okay, so E is greater than 1. Therefore, what do you say? Therefore, the series A sub n diverges by what test? By the limit, by the ratio test. By the ratio test. Okay. So let's try this one. So next example, try this one on your own. It's the sum 3 to the n over n factorial as n goes from 1 and then approaches infinity. And again, I want you to apply, there's other tests you can apply. This is just a section, so apply the ratio test. All right, so try that. So it's a sub n over a sub n plus 1 as n approaches infinity. Oops, reverse that. A sub n plus 1 over a sub n. Okay, so if you do that limit, you do that simplification, you'll get 3 to the n plus 1 over n plus 1 factorial times n factorial over 3 to the n. Okay, and you simplify that. So you get 3 over n plus 1. If you reduce all that, which is equal to 0. So what does that say about the ratio test? It's less than 1, so therefore converges, which is less than 1. Therefore, the series 3 to the n over n factorial converges by the ratio test. Okay. So now, let's look at the root test. So this is the next theorem, which would be probably 14, I'm assuming. Yeah, is the root test. All right, so for the root test, same hypothesis to start. Let a sub n be greater than 0 for all n. And we're going to suppose that the limit of the nth root, this is what makes it interesting, of a sub n as n approaches infinity is equal to L. And you get the same cases, basically. You get 1, so basically all this is the same. So we can just copy all that. Come back down here. And you get those 3 cases. Of course, this is different. This is the root, but it's the same conclusion. So series is convergent, divergent, or inconclusive for the same reasons. Okay. Let's look at some examples of that one. So determine if the series 1 to infinity of 2 to the 3n plus 1 over n to the n converges or diverges. In this case, I'm going to tell you apply the root test. So you say the limit, and then you do the nth root, like that, of everything. So it's 2, let me zoom in, so it's 2 to the 3n plus 1 over n to the n, and that's the nth root as n approaches infinity. Okay, so then you have to go through and simplify all that. That's kind of the power behind it, is it simplifies those powers of n. So that's 2. This is all raised to the 1 over n. That's 2 to the 3n plus 1 over n to the n, which you can see that dramatically helps simplify those powers. So you get the limit, and then that's just going to be 2 to the 3 plus 1 over n, and then as you approach infinity. So what is that going to equal? Take a moment. That has to equal 0. Okay, so if it equals 0, it's less than 1. So therefore, the series a sub n converges by the root test. Okay, next example. Let's look at the series n equals 1 to infinity. So try this one. ln n over n to the n over 2, and all of that raised to the n. Okay, so apply the root test. Okay, so try that one and see what you get. Okay, so you're looking at the limit, ln n over n to the n over 2. And basically, you can see that you're just going to take that limit, essentially. Okay, so this one is raised to the n, and then that's to the 1/2. Or 1/2, 1 over n. So that's the limit, n approaches infinity. Ln n over n to the n over 2. Now that you can show using other techniques. So if you wanted to, you can do the limit of ln x over x to the x over 2. And you may have to do some work on this one to show what happens. But basically what's going to happen here is this denominator is going to grow a lot faster than this numerator. So if you just do one L'Hopital's rule on this, and you'll have to look up how to do that derivative again, you'll get it approaches 0. Okay, so that's going to approach 0, so it has to converge. Okay, so therefore converges, which that's less than 1, by the root test. Okay. So let's see. I had one more to do. No, we're good. We'll probably just do some cleanup, maybe a few more examples. We'll see after this. Okay, I think we're done with most of the tests, and we'll look at 9.6 probably next week, which is the alternating series test and conditional convergence, which has to do with what I've already kind of mentioned. So we've done the heart of everything in the class, or this chapter so far. There's a few more things to do. Then we get to kind of something a little different called power series, Taylor series, and that wraps up chapter 10. So we'll get to that, end of next